Okay, we are on the second half of Unit 2, magnetic forces and fields. So this lesson does not involve any math at all. And here we are. So bar magnets and magnetic field lines. So first of all, bar magnet, rectangular piece of material that generates a magnetic field with distinct north and south poles. If you need extra time to pause to do the definitions, go ahead and pause. Next part. Magnetic field lines, invisible lines that represent the direction and the strength of magnetic field, showing how the magnetic force is distributed around the magnet. Okay, so here we got a couple field lines, and then we're actually going to draw this. So I'll just get this ready to go. Okay. What I have here, pen. Black. Okay, field lines are going to come out of a north, and they are going to go into the south. So what's going to happen? Well, they come out of the north, but they also wrap around. So they're going to do this, going around, out of the north, into the south, and then we kind of get some of these happening as well, okay? So that's what my field lines are going to look like. Okay, so what is happening? Well, we have field lines come out of north, out of the north, and they go into the south. So what happens here? Well, my field line is going to come out of the north and go into the south. So out of the north, into the south, into the south, out of the north. Now I'm still going to get my wraparound part here. Okay. It's going to look like this. And we're still going to get a wraparound part here. Okay, and of course we're going to have it kind of do the same thing that we saw with electric charges in between. Okay. Now, what happens if I have two north ends side by side? So it's going to come out of the north into the south. So I am going to have it come out of the north, wrap around the side, and go into the south. This lesson's a little bit better when we got demos. So out of the north, wrap around the side, into the south. But what's going to happen here is our field lines are not going to do well when they interact with each other. So they're going to kind of push off like that. Rather than the field lines connecting and an attractive force, we get the field lines pushing off each other, we get a repulsive force. Same sort of thing is going to happen when we have south to south. So a field line comes out of the north, wraps around the side, and comes into the south. Wraps around the side into the south. Comes out of the north, wraps around the side and into the south. Okay, and then we're going to have, it's going to look kind of the same, something that looks like this. Okay, so my field lines kind of pushing off against each other. Now, what if I took a bar magnet and were able to bend around to be a horseshoe magnet? Well, in this special case, what I'm going to have is my field line comes out of the north into the south, and I actually get a fairly uniform magnetic field in here. Now, we do get a little bit of kind of wraparound happening like that, but in between there we get more of a uniform magnetic field. Okay, we're going to move on. Pause if you need to. So when I look at the next one here, compasses and field lines. So the north end of the compass will always point in the direction of the magnetic field lines. So if I were to put a compass right here, because the field lines go in that direction, my compass is going to line up in that direction. I were to put a compass right here, because my field lines come around this way, my compass is going to line up with the field lines. So I can see here, my field lines come out of the north. I'm just going to do the superimpose. They come out of the north, they wrap around, and they come back into the south. And my compass is lining up with those field lines the entire time. Now this brings up an interesting question. If the Earth had a giant bar magnet inside, it doesn't, but if it had a giant bar magnet inside, what would the orientation of the bar magnet be? Well, what we do know is if I were to put, I live on the surface of the Earth. If I were to put a compass right here, my north end would point upwards. Fantastic. Now what that means is my field lines are doing this. And field lines come out of a north and go into a south. So keep in mind, the magnetic north would be at the bottom, and the field lines wrap around. I'm on the wraparound section, which is why my north is pointing with the field lines. Okay, moving on. Domain theory and magnetism. So, magnetic domain, a region within a material where the magnetic moments of atoms are aligned in the same direction, resulting in a net magnetic field. So what I have is I have a magnetic substance. There's a whole video on this, but the video goes into excruciating detail about like half-filled orbitals and electron spins. It's really, really worth watching, but it's also way too much detail for what we need in Physics 30. So just know that if I have a magnetic material, I might have a small portion of it pointing one direction, small portion in another. Magnetic, there's no domains. Magnetic materials could have domains where I have a whole section lined up in one direction. So the field line's pointing upwards, a whole section where the field lines are pointing that way, but they're not all aligned. A magnet, all my different domains are lined up, and now I have it actually being magnetic. Now if I crack it, drop it really hard, I might mess up my domains, and then it's still a magnetic material, but it's no longer magnetic. Okay, let's move on. Oersted. Now we're going through this pretty quickly, but yeah, ideally, like I said, lots of demos if this is happening in class. Oersted demonstrating that a moving current generates a magnetic field which deflects the compass from its original direction. When no current was moving, the compass was undeflected. So no current moving, compass not undeflected. As soon as the current runs, all of a sudden the compass will deflect, and the direction of deflection will determine what direction, or based off what direction the current's working. Now we're going to learn a hand rule for this, where I have my electron flow, and I'm going to take my hand and I'm going to orient it correctly. I don't have hands on the bottom of this one, but we are going to learn that in the next slide. We do have a quick video here for you to watch. Please do watch it. Okay, moving on. Electromagnet. A type of magnet created by passing electric current through a coil of wire, which generates a magnetic field around it. So here I've got a coil of wire, nothing is happening. No magnets, just a loop of wire. But if I run current through it, it acts like a magnet. So now it acts like I have a bar magnet inside of it. Why this is useful is I can take something that is not a magnet and I can basically flip it on and off. Flip it on to be a magnet, flip it off to be a not magnet, flip it on to be a magnet. And with this electromagnet, it's not just always magnetic and stuck to things. I can turn it on and off. So how do I increase the strength of it? Well, first of all, I could increase the current through the wire. I can increase the number of loops. I could wrap the coil tighter, or I could use a stronger ferromagnetic material for the core if I got, say, a core in it to begin with. Okay, I'm going to move on. Pause if you need to. So, first hand rule. This is where we're going to involve hand rules. So back in the beginning of Physics 20, depending on how the year started, we may or may not have done this. These are our numeric response for directions. What direction is person A traveling? Well, person A is traveling to the right, which corresponds with number 3. Person B is traveling diagonally downwards, which corresponds to number 1. Person C, diagonally upwards, is going to correspond to 8. Person D, straight down, is going to correspond with number 6. Okay, so 3186 is my correct answer on this. Now, this is all fine, but it only deals with stuff moving up, down, left, right, inside the plane. So what if something was moving towards me? What do these 9 and 0 represent? Okay, so this is where I have this wonderful diagram. Here I've got an arrow going upwards, an arrow going to the right. Now this arrow if it were coming out of the page, would be a circle with a little dot. So that is where I see the dot. That's coming towards me. If it were going into the page, I can see the little feathers here. I would see the circle of this cone with the X. So that's going into the page. This is going to the page. So this one here is out of page right there. That's into page. Now with my hands, because I don't have much of a choice about how I'm doing this would represent into the page because my thumb is going into the page. This would represent coming out of the page because my thumb's going out of the page. This here would now represent going upwards because my thumb's going up, or going to the right because my thumb's going to the right. So this is how I'm going to have to show this to you guys on a pre-recorded lesson. Okay, moving on. So first of all, left-hand rule. I'm going to use left hand for current because it's electrons that move, left hand negative. So when used when a negative charge is moving through the air or through a wire. My straight thumb is my direction of my electron flow, and my curvy fingers are direction of the curvy magnetic field. So here I can see this, my straight thumb in the direction of the straight electron flow, and my fingers are going to wrap around with it. If I were to, let's say I really want to paint my nails, I'm going to draw my thumb and I'm going to draw my fingers. There we go. That is a beautiful drawing. Okay, there's my thumb, and I paint a nail on, or an arrow on it. And then I've got these, and I could paint arrows on them, okay? Or draw an arrow like that. So I've got my straight thumb and my curvy fingers. Fantastic. Now, right-hand rule is going to be when I have a positive charge. Now, this is weird because we get questions like this. Two different wires have electric current flowing through them. Using the number of directions above, determine the direction of the magnetic field at point A, B, C, D. So what I'm going to do is I'm going to grab this hand right here. In this case, my current is going there. And what that means, when I look at my hand, I'm going to have my magnetic field looping around like that. Looping around, well, that's not right. Looping up the back and down the front because my fingers are coming down the front. So that's what that means. Now, as that does that, what I'm going to have is it's going up the back, it's coming out of the page there, it's going down the front, and it's going into the page there. So at point A, so again, big circle, into the page, up the back, out of the page, down the front. And I can see right here, imagine I were holding a cylinder. Okay, there's a cylinder. Kind of shape it around my fingers. My fingers are coming down around the front. My fingers are, there's my fingers right there, if you will. Okay, and my thumb is going that direction. So I have my fingers coming down across the front. So they're coming out of the page here, which means at A, out of the page is a 0, and at B it's going into the page, and that is going to be a 9. Now, if I were to now look at this one, I've got to take my hand and I've got to rotate it so my thumb is in the direction of the current. So thumb, direction of current. There we go. Now for this one, my fingers are coming up the front. So my fingers are coming up the front like that. Okay? And then it's going to go down the back. So up the front. So what that means is coming up the front, it's going into the page here, it's going down the back, and it's coming out of the page right there. So at C, it's going into the page, that's a 9, and D is coming out, and 0990 is going to be my answer. Okay, let's move on. So now we got to practice this over and over and over and over. Okay, I'm going to grab my hand, I'm going to bring my hand up here. So I'm going to do 1 or 2, and then I want you to pause it. I'm just going to shrink this down a little bit. So first of all, thumb going up, left hand, my thumb is going up. Okay, and what I find is my fingers are coming, again, imagine that I am holding something, okay? My fingers are coming across the front like that. So it's going to loop around like that, across the front. And that's what my magnetic field looks like. Second one, I'm going to rotate it so my thumb is going down. Now my fingers are coming across the front like this. So then my loop is going to kind of just loop around like that, coming across the front, going across the back. Now I want you to try the next two. Pause the video, unpause when you are done. Okay, I'm going to assume you are done. Take my thumb, left hand, movement of electrons. I'm going to point my thumb in that direction. And we are coming up the front like that. So my magnetic field is going to be looping around. Next one, weird diagonal. Point my thumb in the direction of the weird diagonal. And again, if I were holding something, what I have is my fingers are coming across like that. And therefore, my magnetic field is going to loop around in that direction. Okay, next one's kind of become weird. Take my hand. I can see that my fingers are coming down across the front. So therefore, my magnetic field is going to loop around in a circle. I'm going to do the other one way over here. Thumb is going in that direction. My fingers are coming down across the front like that. So therefore, my magnetic field is going to loop around like that. Now I've got the 0, or the dot, and the X. So I got to go down to the bottom, and I got to pull this thumb up. This one is coming out of the page, so my thumb is coming out of the page. So if my thumb's coming out of the page, what's happening with my fingers? Well, my fingers are wrapping around like that, so I'm actually going to have a magnetic field that is going to go around like that, looping around. When I look at the X, here is my X. And my fingers are now looping around this way. So they're going to loop around like that. Now, next one. I'm going to have a problem with my protons because I got to use my right hand and I forgot to photograph my right hand. But I want you to do all the non-highlighted ones. So do the non-highlighted ones, pause the video, and unpause when you are done. Okay, gonna assume you have unpaused and you are done. So I'm going to go up and steal my hand here. Electrons going up. Now this time, rather than moving through a wire, it's just an electron moving through space. So that's fine. I can still see that my field is going this way across the front. So it's going to loop around like that. Electron in a wire. All good. Thumb in the direction of motion. And I can see that my fingers are wrapping around the front like that. So that's the direction they're going to go. Let's see. These two are exactly the same because my electron is moving in that direction. I'm going to be looping around like that. So I'm going to loop down across the front and I'm going to get a circular magnetic field. Or if I have a whole series of them in a wire, same idea. Looping down across the front. So I'm looping down across the front and up the back. Now the issue becomes a proton. Well, what's a proton going to do? It's going to do the opposite. So I have to use my right hand, which I do not have illustrated. But if I use my right hand, I should... Okay, good time to poorly draw right hand. My right hand is going to look like this. There's my thumb. And then my fingers are going to look like that. So this is my right hand. As a result, I'm going to have it coming down the front and up the back. Same thing, poorly drawn right hand. Oh my goodness, I'm just going to make my life easy. Clone. Nope, that's not what I want to do. Just this guy. Clone. There we go. Going down. I should get something that looks like that. It's going across the front, around the back. Okay, let's move on. So now we're on the second hand rule. Now the first hand rule back here is when I have a straight moving current and as a result I get a circular magnetic field. Second hand rule is going to be the opposite. I'm going to have a circular current and a straight magnetic field. Now, how does this work? What I'm going to do, where is my hand? I'm going to go back and take my hand. Give me 1 second here. I need this hand, and I'm going to copy it and edit, paste. Nope, because it does not like me and it did not copy. Let's try going back here. Sorry for the quality of this. I am trying to make this work. It's kind of a pain. Copy, edit, paste. Okay. So what I have here is I'm going to have something that looks like this. Now, in this case, just to give you a quick overview of how it's going to work, I've got a circular current, and therefore I've got a straight magnetic field coming out of the middle. Now, if I look at it as a small little section, so if I take this section here and I draw it here, I could say that I have more or less a straight current, and as a result, my hand's going to loop around, and we're going to have the magnetic field coming out of there and going into there. Again, straight current right here, straight current. I'm going to have my magnetic field coming out of the middle, and it's going to loop back around. And again, straight current for this section here. I'm going to have it coming out of the middle and going in there. Now, when I do all of that, what I find is it keeps coming out of the middle the entire time. I'm going to try to draw a 3D bar magnet to explain something here. This is my bar magnet, and this is my north, and this is my south. My field line is going to come out of the middle there, and it's going to wrap around the back and go into the back like that, okay? That's essentially what we're seeing. We're seeing all of that magnetic field line coming out of the middle and then wrapping around the back. Now, rather than have to do this little analysis where I do first hand rule, first hand rule, first hand rule, I could take my second hand rule and say, well, if I've got a curvy current, then I got a straight magnetic field. I'm going to use B for magnetic field. Okay, let's move on. So second hand rule, curvy fingers, direction of electron flow, straight thumb, direction of the straight magnetic field through the center of the loop. Well, let's practice this. I've got a bunch of hands down here. The first thing I need to do is I need to figure out what's happening with my current. So current always comes out of the negative terminal. So my current is going to do this, and it's going to go around like that. Now I've got to match a hand up to it. So I'm going to go down, I'm going to take this hand right here. And what I find is I find my fingers are going across the front. Here, my fingers are going in the wrong direction. Now, if I do this, my fingers, when I'm looking at it, are going across the front like that, the same way my current's going across the front. And what that means is because my thumb is going down, my north end of the field line is coming down. Now, in blue, I could then be like, and it wraps around the side and goes into the south, okay? But the main part here is that the north end points down. So now we're going to look at this next one. Current comes out of the negative, and it's going to go this way. So I take my hand. I got to rotate my hand until my fingers are wrapping around in the same direction. So in this case here, my current is now wrapping around in the same direction, and my thumb's pointing up, so my north end of the magnet is going to be upwards. Okay, let's look at the next two. Now, what determines up or down? It's not the battery orientation, it's not the wind, it's both of them together, okay? So this time we got the current coming out of the top. Current coming out of the top, goes around the back, gonna follow the lines through. Okay, so I need to get my fingers wrapped around the front. These ones, they wrap around the front, and therefore my north end is up. Okay, I want you to try the next one on your own. Pause the video, unpause when you're done. Okay, you're gonna see unpaused, out of the negative, we got our current, and it is gonna go like this. So it's gonna wrap around and then come back into the positive terminal. So I'm going to take my hand, I'm going to wrap my fingers around. Right now they're backwards. I tilt my wrist downwards. I can see that my current is now wrapped around in the correct direction, and we've got a north facing down. And again, the field lines will wrap around and into the south. Okay, these two here, I want you to try them 100% on your own. Pause the video, unpause when you're done. Okay, I'm going to assume that you are done. Well, I need to get my fingers wrapped around this direction. This does not wrap them in the right direction. This one does. Now, because that wraps them in the right direction, my fingers are going around in that direction. My thumb is coming out of the page, and that means that my north end is coming out of the page. Yes, it will wrap around the side, and it will come in like that and come in through the other side, but big thing here is just that north coming up through the center. For the second one, I need my fingers to wrap in the other direction, so if I tilt my hand downwards, just like that, then I notice my thumb is pointing into the page and my magnetic field is pointing into the page at that point. Okay, almost done. Now, if you have a problem with any part of this lesson, it's probably going to be, Mr. Bear, the current doesn't come out of the negative terminal. And you'd be wrong, because the current most definitely comes out of the negative terminal. But unfortunately, we got a bit of a problem. Conventional current. This is what I learned in British Columbia when I was in school. This is what's used in electronic design at university. And this is what you probably learn in automotive. Current comes out of the positive terminal. Here's the truth, and you hopefully remember this from grade 9. Current requires a complete circuit to run. So if we got a complete circuit, who knows what terminal it's coming out of, because it needs to be a complete circuit. Anything other than a complete circuit, no current running. So the concept of conventional current, where current flows from positive and negative, was established in the 18th century by Benjamin Franklin, who was wrong. Despite the discovery of electron flow direction, negative to positive, in the late 19th century, conventional current notation is still commonly used today. We do not use it in Alberta. As far as we're concerned, current always involves the movement of electrons, which is the factual truth, from negative to positive. So, what is it? Current type. Electrical current, the correct knowledge that electrons move from the negative terminal. Conventional current, the incorrect belief that electrons move from the positive terminal. When I'm using movement of electrons, I use left-hand rule. When I have positive charges moving, I use the right-hand rule. And what result does it give? Well, let's look at the correct one. It comes out of the negative terminal. Okay, I'm going to take my left hand, which I'm going to draw very, very poorly, and I apologize. And my left hand is going to look like this. There's my thumb. Okay, and my fingers are going to wrap around like that, okay? So what I've got, this is left hand. I've got my fingers wrapping around like that, which is exactly what we see, and we have our north end pointing down. Fantastic. Now, conventional current, also known as wrong. My current comes out of the positive terminal. Not right. But then I need to use my right-hand rule. So I need to take my right hand and do that. And I'm going to have my thumb going down. And I'm going to have my bumpy fingers. And my bumpy fingers are going to wrap around like that. So once again, I've got my current going in that direction and my thumb pointing down, and we get the exact same result. So conventional current works, but it's not something you're going to see on diploma. Now, the reason I'm stressing this to you is conventional current's used in British Columbia, it's used in portions of the States, it's used in automotive, it's used in circuit design, and as a result, they refer to current as right-hand rule. If you go on in the internet, if you hop on YouTube and you search for hand rules, you're going to find right-hand rule. Hey, that's not how Mr. Bear did it. He didn't use the right-hand rule. Correct, because we dealt with the actual flow of electrons, which is what we test and assess in Alberta, because it's what's factually accurate. You have to be using left-hand rule. This is the one area where I'm going to strongly suggest that you do not use the internet, okay? Now again, right-hand rule gives this result, but if I were to say electron flow moving downwards, which is correct, and I take my left hand, I get the same circular magnetic field, which, just as a side note, if I were to put a compass here, it would line up in that direction. If I were to put a compass here, it would line up in that direction. Compass here would line up in that direction, and a compass here would line up in that direction. Now, that brings us to the end of today's lesson. If I go back over to here, and I search for worksheet, we do have a worksheet. I just want to talk about what this worksheet looks like real quick. If it will open any minute now. Okay, we've got a quick review. There's no textbook questions. We got a couple diploma questions. They're pretty straightforward. They don't involve a lot of math. I strongly recommend doing these ones, even including these ones at the end. There's not a whole bunch. It is incredibly worth it for you to do. This is a confusing topic for some people. If it's an area that you're not understanding, please come see me. We can quickly hammer out 50 of these things in like 5 minutes, okay? So if you're not getting it, come see me immediately. Thank you very much.